this is quite interesting. A very brief talk about GPS satellites and the fact that we need to correct their clocks because of relativity. A lot of flat earthers and deniers of gravity and so on think that gravity doesn't exist and so on and so forth. But if there ever was a proof other than just dropping an object onto Earth, this is one. Not only that, but it's proof of Einstein's equations as well. So without these equations we've got here, which I'm just going to show you, GPS satellites would give inaccurate results. That's because the clock, that's the digital clock, would run at the wrong frequency or the wrong time. And although this sounds sort of counterintuitive, you might imagine that some mechanical clock might run slower or something. How on earth can a digital clock do it as well? It's really any clock, it doesn't matter, will run at a different rate. So we've got to consider both special relativity and general relativity. Now we don't actually need to know all about, the tensor calculus and stuff like that in general relativity, but special relativity is relatively easy. Now we know the speed that these satellites go at. It's 3,874 meters per second. Speed of light is 3 times 10 to the 8 meters per second. It's better to use SI units here. I mean, you don't have to, but it's better. And the altitude, they're at about 20,000 kilometers. I think it's 20,200 that they're at. So first of all, special relativity. What that does is, as you get faster and faster and near to the speed of light, you suffer what's called time dilation, where time slows down relative to an observer on Earth. Now you can't really do much, with a satellite because it's not exactly going at speeds close to the speed of light, but nevertheless it is going at a velocity, and there is a slight slowing down of time due to special relativity. We can work that out using this formula here. It's just this time dilation, square root of 1 minus v squared over c squared, where v is the actual velocity of the satellite and c is the speed of light. And we work out that from this, that the GPS satellite clocks tick 7.2 microseconds slower per day due to their speed. Now, that might not sound very much, is it? 7.2 microseconds. I mean, you're not going to even notice that on a house clock, are you? But you do notice it with the GPS. But that's not the whole answer. I mean, I used to think that's it. But there's general relativity as well. Now, what that is we can use this equation near Earth. You need metric tensors and so on if you're going to be near black holes and so on. But we can use this thing here, and this is square root of 1 minus 2 gm. G is the gravitational constant, m is the mass of the Earth, r is the radius you are from the Earth, and c is the speed of light. And it turns out that the closer you are to a gravitational field, again, time slows down. But in this case, we're actually further away because the satellite is further away from the Earth, so there's less gravity on the satellite than there would be if it was sitting on the Earth. So with general relativity, there's also a slowing down, but in this case, because it's further away, it's actually speeding up. It's further away from Earth. So if further you go into space, your clock slows down as well due to general relativity because there's less gravity. It speeds up, I beg your pardon. As you get closer to gravity, it slows down. But because the GPS satellite is further away, it actually speeds up. So you've got a speeding up and a slowing down. Speeding up due to general relativity and a slowing down due to special relativity. So you can work this one out as well. It's not difficult. That's a school kind of maths problem. We know the gravitational constant. We know the mass of the Earth, 5.9 times 10 to the 24 kilograms. And we know the radius of Earth. We know the orbit. It's about 20,200 kilometers. So we can compute this time dilation at the Earth's surface, and then we can compute at the GPS altitude and work out the difference in the times. and that works out to be 5.28 times 10 to the minus 10. Again, a very, very small number. So over one day, though, you get 45.6 microseconds gain. So the special relativity slows down the clock by 7.2 microseconds per day, and the general relativity speeds it up by 45.6 microseconds per day. So you get a net gain of 38.4 microseconds in a day, which is very interesting, isn't it? So that means that engineers have got to, before launch, they actually adjust the clock so that it's to account for this. The clock correction is 4.5 millihertz, that is, not megahertz, for a 10.23 megahertz clock. And of course that's also proof of that Einstein was correct. And you can have all sorts of fun now with general relativity, because you can consider flying around just outside black holes and so on to see the effect of, and neutron stars, to see the effect of gravity. I don't mean going into them, but I mean if you get close enough to a safe region, which again you can work out what that is, you can work out time dilation, and that gets even more interesting. But for the moment, that's the GPS thing, and you need to adjust for the clock. Just sum it up. Special relativity slows the clock down by 7.2 microseconds per day. General relativity speeds it up by 45.6 microseconds per day. The net gain is 38.4 microseconds per day. So they've got to slow it down because it goes net positive. Over a week, of course, that mounts up. You might not think it's very much, but it does over a week. Thank you.